Since humans began observing the sky, a question has crossed time, cultures, and civilizations. Where do we come from? How did life originate on Earth? This is not just a scientific curiosity, it is an existential question. Understanding the origin of life is understanding who we are, how we got here, and what our place is in the universe. Modern science proposes that life originated here on our planet about 4 billion years ago. In a hostile, hot, and chemically active environment, simple molecules gradually combined, forming increasingly complex organic compounds until the first self-replicating cell appeared. This explanation is known as abiogenesis. It suggests that life arose from non-living matter, driven by energy, time, and favorable environmental conditions. Classic experiments have shown that amino acids and other essential molecules can spontaneously form in environments similar to primitive Earth. But there is an alternative hypothesis that extends this story far beyond our planet, a hypothesis that shifts the origin of life from Earth to the cosmos itself. This idea is known as Panspermia. The word Panspermia comes from Greek and means seeds everywhere. According to this hypothesis, the universe would be filled with biological or pre-biological material, spread among stars, planets, moons, and solar systems, ready to give rise to life when the right conditions are met. This idea is not recent. More than 2,000 years ago, Greek philosophers were already speculating that life could have a cosmic origin. Anaxagoras spoke of universal seeds distributed throughout the universe, responsible for the emergence of life in different worlds. For centuries, this hypothesis remained confined to philosophy. There were no tools to test it, nor sufficient scientific knowledge to take it beyond speculation. But that began to change with the advancement of astronomy, chemistry, and biology. In the 19th century, scientists began to realize how unlikely the spontaneous emergence of life from inanimate matter seemed. The extreme complexity of the cell, even in the simplest forms, raised profound doubts. At the beginning of the 20th century, Swedish physicist and chemist Svante Arrhenius proposed a scientific version of panspermia. He suggested that microscopic spores could travel through space propelled by the pressure of radiation emitted by stars. This hypothesis became known as radiopanspermia. According to Arrhenius, extremely small particles could escape a planet's gravity and traverse interstellar distances over millions of years. Over time, other variants of panspermia have been proposed. One of the most discussed involves meteorites, asteroids, and comets as natural vehicles for the transport of life. This version is known as lithopanspermia. In it, fragments of rock ejected from a planet by violent impacts could carry microorganisms protected inside, surviving the journey through space and entry into another world. Recent discoveries have given new breath to this hypothesis. Meteorites found on Earth contain amino acids, sugars, nitrogenous bases, and other fundamental organic molecules for life. This demonstrated that the basic building blocks of life are not exclusive to our planet. They naturally form in space environments, within interstellar clouds, comets, and asteroids. Comets, in particular, are considered reservoirs rich in water and organic compounds. During the intense bombardment that occurred in the early stages of Earth, numerous comets may have struck the planet, delivering these essential ingredients. Experiments conducted outside Earth revealed something even more astonishing. Microorganisms exposed to space can survive vacuum, intense radiation, and extreme temperature variations for extended periods. On Earth, bacteria known as extremophiles thrive in environments considered hostile, such as hydrothermal vents, icy deserts, and highly radioactive regions. This shows that life is much more resilient than previously thought. These discoveries radically expanded the concept of habitability. Environments previously considered sterile are now seen as potential cradles of life. Mars is one of the main candidates for a direct connection to the origin of terrestrial life. Evidence indicates that it once had oceans, rivers, and a milder climate in the past. Martian fragments have already been found on Earth. This proves that material can naturally travel between planets, making the exchange of organic compounds or even microorganisms plausible. Like Europe and Enceladus, they have underground oceans heated by gravitational forces. These environments offer liquid water, energy, and chemical compounds, three essential ingredients for life. If life can emerge or survive in these worlds, panspermia ceases to be just an exotic hypothesis and becomes a concrete possibility within astrobiology. If panspermia is correct, life would not be a rare or isolated event. It would be a natural consequence of the universe itself, always emerging whenever conditions permit. This profoundly changes our view of the cosmos. Life would not be an exception, but a rule. It is important to emphasize that panspermia does not explain how life originally arose. It only suggests that its origin may not have occurred on Earth. The final question remains open. Was life born here, or was the Earth just another stopping point in a much larger cosmic journey? If this video impacted you and sparked new questions about our origin and the universe, new discoveries keep emerging. Follow us.